We're going to do a couple of practice problems before we get really in depth into the SN2 mechanism. Um, so the first one here, go ahead and copy this down. So when we're dealing with nucleophilic substitution, you always want to identify both your nucleophile and leaving group so that you know where everything is supposed to go. Now, most commonly, your best leaving groups are the halogens. So we're going to assume this right here is our leaving group. Now, we will talk a little bit about other leaving groups that aren't halogens, but those are the most common ones. And then our nucleophile is going to be something that has some negative character to it. So if we look at what's above the reaction arrow here, we have CN, which is cyanide, the CN minus ion, that carbon's negatively charged. And the sodium is the cation. A lot of times we don't care about the sodium. It's a spectator ion. So whether or not you show it in the reactants or products, it does not matter to me. Just don't be surprised when you're going through homework or problem sets or on an exam, you see that positive ion. It does not play any role. You can kind of ignore it when it comes to the reaction itself. So we're going to assume, as the problem says here, we're doing an SN2. So that means we're going to replace the chlorine with the nucleophile. But because it's SN2 and that is a chiral center, the leaving group is on a chiral carbon, then I'm going to not only replace the chlorine, I'm going to have the leaving group come in from the opposite direction to get that inversion of stereochemistry. Now let's look at another example here. And I'm going to kind of put in a red herring, and I'll show you why here in a second. Do it like this. I'll just say ethyl group. Now again, let's identify our leaving group. So here's our leaving group. And what's going to replace it? Well, OH is hydroxide. That's a pretty good nucleophile. Again, we don't care about the sodium cation or that positive cation. We don't care about it. And I know that I'm just going to replace the leaving group with the nucleophile. Now I'm going to look at the carbon it's attached to. Is that chiral? That's not a chiral center. And you say, well, wait a second, there's a chiral center elsewhere. I mean, this is a chiral carbon right here. That's great, but it doesn't play any role in the reaction. I'm not going to change the configuration around that carbon because it plays no role in the reaction. The reaction happens at the carbon with the leaving group. So that is all going to stay the same. And I'm just going to replace the bromine with the OH. All right, so let's kind of dive a little bit deeper and talk about some things that affect the rate of an SN2. One of the skills you need to develop is to be able to look at a series of reactions and judge what their relative rates would be. Like if you have three reactions, you should be able to order them in from like slowest to fastest or vice versa. And one of the ways that we judge that in an SN2 is by looking at the structure of the substrate or where that leaving group is at. And what I mean by this is what is around the carbon with the leaving group. So let's look at this table right here. And we're doing this generic reaction, replacing the bromine with an iodine. And we can see that there is a difference in rate based on what is on this alpha carbon. That term alpha, I'm just referring to the carbon with the leaving group. So if it's just hydrogens, that's a pretty fast reaction. If it's primary, then that's kind of like our standard. You know, we say a rate of one and everything else is compared to that. If it's secondary, that's a lot slower. But if it's tertiary, there's no reaction that happens at all. So there's no noticeable substitution product. Now, let's try to explain this. This is the what happens. I'd like you to also know why this happens. All right, so let's look at, this is not the specific example. This is with using hydroxide as the nucleophile, but same thing. When the nucleophile attacks a primary carbon, you can kind of see here, I'll try to highlight, in green there. It can kind of see that carbon right there. That's the carbon with the leaving group. And then if it tries to attack a secondary carbon, it can still see it a little bit. But because of all the steric bulk around a tertiary carbon, attack is impossible. It can't even see, the nucleophile can't even see the carbon with the leaving group. So there's no possible way it can make a bond to it. So the rate of an SN2 is affected by, number one, the number of substituents on the alpha carbon. Why? Because it deals with sterics. If there's too much steric bulk, then the nucleophile can't see the carbon with the leaving group, and it can't make a bond with it. Now, there's a second factor that the rate is affected by. This is not as drastic. So the first rule that I wrote there, not really a rule, but the first point is the most important in determining the rate. The second one is kind of secondary. It's not as big of an effect, but it is a noticeable effect. And that's if there's things on the beta carbon. So if the carbon with the leaving group is alpha, the next carbon over is beta. So if there's just, hydrogens on that beta carbon, we give that a relative rate of 1. That's like the standard. If there's one group on that beta carbon, it slows down a little bit. If there's two groups, it slows down a lot more. And if there's three groups, it slows down a whole lot more. It doesn't completely shut it down, but it just creates more steric bulk close to the carbon that has the leaving group. So the other thing that affects the rate of an SN2 is the number of substituents on the beta carbon. And again, I want to highlight that this is not as big of an effect, but it still has somewhat of a noticeable effect. So the main thing that we look at for comparing rates of SN2 is what's on the alpha carbon. Because a methyl is faster than primary, which is faster than secondary, and doesn't even happen on tertiary. Now let's talk a little bit about drawing the transition state for an SN2. So here's the reaction we're going to operate on. So our nucleophile, well, actually the first thing we want to do is identify the nucleophile and the leaving group. Why do we want to do that? Because that's where the bonds are forming and breaking. So then the second step in drawing the transition state is we use dotted lines to show bonds breaking and forming. So right now I'm just going to show this right here, that carbon. So there it is. And I'm going to show the nucleophile making a bond to that carbon. That nucleophile's a little negative. And then I'm going to show the bond breaking between the carbon and the leaving group. Now to finish this off, I'm going to put the rest of the stuff on this middle carbon right here. So step three is give one group a solid line, one group a dashed wedge, and one group a solid wedge. Now, as a side note, if the carbon with the leaving group is not chiral, it doesn't matter what bonds you assign to the transition state. Meaning, it doesn't matter which group you give the solid bond or the solid line, or it doesn't matter which group you give the dashed wedge or the solid wedge, as long as it's not chiral. If it is chiral, then you just follow what the stereochemistry says. Whatever group has the solid wedge, you give it that wedge in the transition state. Whichever has the dashed wedge, that's what you give it in the transition state. So you're going to draw some brackets. I show the nucleophile making a bond to the carbon, the leaving group breaking the bond to that carbon, and then I give one group a solid line, another group a solid wedge, and the other one a dashed wedge. Again, all of this right here, this group and these groups are this here, and then the hydrogen and the hydrogen there. And because the carbon with the leaving group is not chiral, it does not matter which one I gave the solid wedge, dashed wedge, or the solid line. And then I put the whole thing in brackets and then use this kind of marking to indicate that this is a transition state.